Start the recording. For those of you who are watching the video, a very warm welcome to you. Thank you for sparing your time to join us on this session today. Today's session is, I think it's the advantages and disadvantages of signal averaging. Actually, the advantages outweigh the disadvantages, so maybe a better title would be to say the considerations of signal averaging. What we're going to do over the next hour is to cover the types of averaging. We'll talk about linear averaging, exponential, peak hold, synchronous time averaging, which is a really powerful method of extracting a signal that we're interested in. And we'll finish off with a special case, and that is considerations when we're looking at very long time intervals between a signal, very low speed machines, and along that time interval between our events that we want to measure. So without any more ado, we'll move on. First of all, one consideration is whether to average or not. It's an important one because averaging does take time, and if time is of the essence to you, you need to give it some thought. I'm thinking here in terms of doing route-based data collection or route-based data collection. If you're going to go off and collect 2,000 measurements and you spend time averaging each and every one of those measurements, it can take a long time. If you're taking 10 or 15 measurements, multiply that by 2,000 measurements, you're going to be out walking around for a very long time. So with some careful thought and careful consideration, you can decide whether or not averaging is a good thing for you or not. Some machines are inherently stable. The levels don't move up or down an awful lot. They're steady. And I come from the good old days of moving needle displays, where your vibration meter or your sound level meter had a needle. And this inherently required a certain degree of common sense. And quite often you'd see the needle and it's barely moving. And that would be the case for simple electric motors, fans, some types of pump. You'll look at the spectrum and the line in the spectrum is rock steady. So there's very little point in averaging that signal if it's rock steady. Going back to my moving needle display, sometimes you do a vibration survey and the needle would be moving, and you would eyeball average. You'd put your eye through it and say, well, reading's that. Or you could turn a switch, and that would put a capacitor into the line, a larger capacitor, and that would minimize the oscillation. And effectively, you're averaging using electrical components. You can do exactly the same mathematically. So there are some machines that inherently generate a varying signal. And we're going to have some examples of that. We'll look at cavitation, we'll look at beat frequencies. So there are some machines that generate a random, chaotic type of signal, witnessed by the needle moving backwards and forwards, and witnessed by the peaks in your spectrum moving up and down. And on that occasion, it might be necessary to think about dialing in some averaging. And it's a balancing act. We're going to be looking at statistics and data, and as I said, you would think that throwing lots of averages at a problem would be a good thing. You get better resolution, better statistical accuracy, but the trade-off is the length of time it's going to take to do your survey and the length of time it's going to take to do your measurements. So we need to think about it carefully rather than just glibly going ahead. I showed you a peak in a spectrum, so we've got a spectrum there with a peak in there. So we're going to be averaging the height of the peak, and we'll start with the first type of averager. Some instruments on the market, it depends on what colour, what manufacturer you have. Some will call it a linear average, and some, practically most, will call it an RMS averager. And it's really simple. A good analogy would be to measure the height of people. So if I took 5 people, I wanted to measure their average height. I would measure their heights, divide by the number of people, in this case 5, and I could work out the average height of those people. Now that's a small cross section. So I might decide that's not representative of that particular sample. So I might decide to measure the height of a bigger cross section. Some nationalities are taller or shorter than others. I won't mention nationalities, which nationalities, but we might decide that 5 people out of a country that has 60 million might not be representative. So we might take the average of 10 or 100 people. And you can see there clearly to measure the height of 10 or 100 people is going to take longer than it does 5. So it's a trade-off. When it comes back to doing it with spectra, all you're doing is taking a series of measurements, one after the other. You take your spectrum, you measure the height of the peak, take the next spectrum, measure the height, put it into memory, and where have I got? 1, 2, 3, 7 spectra there. So you add them all together, and you divide by the number of spectra, and that is your average height. Not forgetting, of course, that we might be dealing with a 400 line, 800 line, 1600 line spectrum, where we've got 400 numbers. So this process does it for every single peak in your spectrum. But I'm just using the height analogy just to get that message across. How many averages should you use is a frequently asked question. As I've already intimated, it depends on how steady state your signal is. If it's really rock steady, it's arguable that no averaging is necessary at all. That one measurement might be adequate. Even if it's steady, I think I might be tempted to do 2 or 3, and I know many very reputable learned colleagues that would maybe take 2 or 3 measurements. But some machines, you inherently get quite a bit of variation. It's witnessed in the old days of moving needles. You would see the needle swinging backwards and forwards, and that's your cue, your evidence that you need to average that signal. And that the same would happen. I've seen peaks in spectra going up and down. I think I do have at this stage a little demonstration of that for you, so you can hear it. In the background here, I've got 2 machines. I've got a driving machine, which is an electric motor, through a belt drive into a driven machine. And because the pulleys are slightly different diameters, there's a slight speed difference between the 2 machines, and we're going to see this later on. I'm going to show you a beat frequency where the levels vary a lot. You can actually audibly hear the signal. So I'll fire this up. What I want you to do is use your ears to listen to the signal and listen how it's modulating. What else would you use other than your ears, you ask? What the heck? So I just want you to hear how this signal is modulating. There we go. So if I slow the machine down, you can hear the signals modulating, and that's audible evidence that the signal's varying, and that's your cue that you might want to dial in some averages. It depends on how long that modulation occurs over. Some machines you can hear the levels going up and down over a long period of time. When you go on your holidays and fly on an aircraft, just listen to what the engines are doing, especially a twin-engine aircraft. If you listen carefully and feel the vibration of your seat, you can feel the levels go up and feel the levels go down as those 2 engines interfere with each other, and that can be over a 5-second period. So one way of answering the question of how many averages, you should be throwing in enough averages to cover that time period, and that time period can be quite long. So these beat frequencies that I've just demonstrated, they can be quite long, and that would require quite a number of averages. Some instruments on the market will allow you just to actually dial in the time. You won't say 100 averages, you'll say this signal is varying over a 5-second period, therefore I want you to average for 10 seconds. Enough, I hear you cry. Just before we move on from the number of averages, for those of you who are mathematically inclined, well done. I am afraid I am mathematically inept. Sorry about that. But years and years ago, I used to do shaker testing of components where we would take a box of electronics and we'd expose it to random vibration. And there was the same trade-off. We wanted to get the vibration signal correct within the shortest period of time, statistically correct. So we used to be looking at random vibration using shaker control systems. and I asked a colleague, what's the best number of averages when you're averaging a random signal? And I was shown this thing, which is the chi-squared graph. This is an example of a graph I've taken off Wikipedia, so I credit Geek3. So this is a chi-squared graph, which I've taken off Wikipedia. I'm afraid my eyes glaze over when I see mathematics, and a colleague gave me an absolutely fantastic, simplistic explanation of what these graphs are telling you. We've got two graphs. The upper graph you can interpret as lack of confidence, and the lower graph is the inverse of that, and we can interpret it as confidence. On the x-axis, on the shaker control system, we had what's called degrees of freedom, and the only thing you need to know is that 2 degrees of freedom is one average. So if you have one average, that's 2 degrees of freedom. And I used to deal with the lime green coloured curve, so that's the only one I'm going to concentrate on. So as you increase the number of averages, the confidence that your data is statistically correct increases, and your confidence that it's wrong also increases as there's a negative number. Gets fun, doesn't it? Or your lack of confidence decreases. So it's you can be on part of the graph, and you can be 90% confident that the reading that you have is representative, and you can be 10% confident that it's wrong. Great fun. As I said, my eyes glaze over, so the magic number that you need to know, ladies and gentlemen, is 8. Excuse me a second. Sorry. Terribly sorry about that. I'm of an age where my vocal cords need lubrication quite a lot. I must remember to have the water beside me. So, 8, ladies and gentlemen, is the magic number. It's on the cusp, on the apex of this curve. So you might say, well, I might as well throw 50, 100, 200 averages at this random signal. But the return on your investment diminishes. So as far as statistical accuracy goes, you don't get much back. So if you're in any doubt, use the number 8, and you should be okay. And that's for those of you who love maths. So now I have a little demonstration for you, starting with a couple of examples. This is an argument which says that averaging improves your signal to noise. And it does, it works if, and I emphasize the word if, you have a tonal type of signal sitting on top of a random type of signal, a random background. I've got a few examples for you. For the classroom, I have a random signal. That is a hissing noise from a radio. That's random sound. And I have a pure tone. So I have a sound level calibrator. So there is a pure tone. And there, whoops, daisy, there is random. And when you mix the two, you're trying to pull one out from the other. And the general idea is that when you start averaging, here's your tonal signal buried inside your random background. It's very, very difficult to see whether there's a tone there or not. When you start to average, and I've taken the average there of 30 spectra, the random part starts to average to its mean position. But the tone is there on the first measurement, it's there on the second measurement, it's there on the third measurement. So now the tone starts to stick its head up above the random background. So I have a little demonstration to relieve the boredom of PowerPoint. I've got an electric motor here which I can bring into shot. So there's an electric motor. I'll attach an accelerometer, so we'll take a reading off this electric motor. I've got it plugged into my analyzer, so you need to be able to see the analyzer. So we'll flag that up for you. There's my analyzer. So I'm going to start by using, here's the averager control, and you'll see there's these types of averaging that I'm going to talk about. So the first is an RMS averager, and that will take the number of averages that I've told it to, and then stop. And I've told it to take 10 averages. I am going to talk about this thing that says overlap, and I am going to talk about this thing that says Hanning, but for the time being, we're here, RMS, 10 averages. So now I can switch my machine on. I have the discs pointing away from me for any safety officers watching. I'm not wearing safety glasses, but the discs are pointing away. So I've started my machine up, it's rotating. It's run up. And I can now start taking my measurement, which is a great cue for another drink of water. Excellent. So there's my spectrum, as I would expect. If I put the cursor on this large peak here, I've just pressed the 7 key, it should hop. So I'm in the UK, our supply frequency is 50 Hertz. So the shaft is running at 3,000 revolutions per minute. If you're listening or watching in the Americas, you might get 60 Hertz. But the thing to note, look at the value there, 0.4 G RMS, and that value isn't varying an awful lot. It's rock steady, and that is a classic example of rotor unbalance. And if you saw a signal that was that steady, that stationary, that deterministic, there really wouldn't be much point in averaging. You might take 2 or 3 averages just so you can tick the box that you've averaged, but there's very little point. One measurement would be perfectly adequate. If we take it one stage further, what I want you to do is put your eyeballs on this part of the spectrum over here, and you will see a peak. Sometimes it's the same height as all the other peaks, and sometimes it gets a little bit bigger. And the level of that is varying, and it's not possible at this stage to determine whether that's actually random kind of background hiss that you'd normally get off a machine, or whether that's actually a peak. So now what I can do now is switch on my averager. This is a real-time, what they call a real-time display. It's just updating on the fly. I have a button which says average. So when I push the button, it's going to take 10 measurements and stop. So I push the button, and it will now hopefully count up. Is it going to do it on this occasion? Yes. Oh, it's done it faster than the display can update. But now that's the end of my RMS average. I can get rid of the noise. And you can see that peak over there is now averaged to its mean position, and it does in fact stick its head up a little bit above all the rest. So averaging on that occasion was useful. And if we go back to our PowerPoint, what that turns out to be is the rotor bar passing frequency. So the first stage to clean the signal up was looking for that tonal, and it's a very tiny tonal, sitting on a random background noise. The first stage is to average it. That gets me a more representative signal. It suppresses the random part of the signal. And on this case, I just changed the y-axis scale from a linear scale to a logarithmic scale. And that's the usual step. If you're trying to see something very tiny, you can change the display to a logarithmic scale, either as a log graph paper or dBs, whichever rocks your boat. So that's that one. What's next? Oh yes, the next type of averager, the exponential average. And I've got another little demonstration for you for that. It's one of my favourite averages. Because with the RMS averager, you've just seen that what I've done is I've taken 10 averages, it's stopped, and I now can press the save key and store that data. And that's possibly the most frequently used averager, because when you're doing route-based data collection, route-based data collection, you're taking your 10 averages or 8 averages or 3 averages, whatever you've decided to do. You take your averages, it freezes, you store the data, you move on. When I'm doing investigative work, when I'm invited to do consultative work, and I just want to roam around and change things and see what's going on, a moving average is actually very useful. And that's if you go back to measuring the height of people, you could take a sample, and that sample can be moving. So what you're doing in a moving average is you're taking 10 averages, for example, and then you take an 11th and throw away the first. You take a 12th and throw away the second. You take a 13th and throw away the third, and so on. So you've got 10 averages, so your data is statistically correct. You can find those tones, but the picture moves, and that allows you to roam with your accelerometer, change settings, So I've got a little demonstration of that for you. We'll just lose the electric motor for the time being. And what I've got is another example of sign on random. So I mentioned that you can improve signal to noise. Here's a classic example. This is a generator in a hydroelectric power station. You've got billions of gallons of water rushing through a pipe. You'll get a roaring noise, a low frequency random vibration from that. And often that gets fed through to the machine of interest, the generator. So the first weapon in our armory is to average, and I'm going to create a similar signal. I am going to do some cavitation for you. So I've got in the background here, I've got a motor pump set, and I'm going to make the signal cavitate. You can't see it in the background here, but this is my cue to change accelerometers, which I have done. So I'll plug the accelerometer in, and we'll do an exponential average of cavitation so you can see this process. So I just need to set that up. So we'll go back to my settings. We recall. I need to change the sensor because this is a different type of sensor. It's a small PCB type. I'll stay with acceleration. Now this is a high frequency pump, so I'm going to measure to 10 kilohertz. Whoops, daisy. 10 kilohertz. And I need to go to my averager section, and I'm going to come down here. With it being 10 kilohertz, I'll probably do it over 800 lines. Now then, I'm going to check 800 lines. Sorry, there's a time lag. 800 lines. So I'm going to change the averager type to exponential. So I've got an exponential averager. I've got 10 averages, and I've got 50% overlap. I might just get rid of that for the time being. I'll come back to that. So now that should be good. The word exponential, by the way, comes from the fact that the latest measurements are given more emphasis than the older measurements. The idea is newer measurements will be factored to give you a faster update rate, and that's where the word exponential comes from. But it's a moving average. So what I can do is I'm going to start my pump, and then start my measurement, and then we'll dial in some cavitation. So press start, slurp of water. Wonderful. So there you can see that's the real-time spectrum, and one of the reasons why I use this machine is, not surprisingly, the speed is fluctuating slightly, and you've got to be careful when you're averaging, because if it fluctuates too much during your measurement, you'll get what's called smearing. So you need to keep an eye on that and make your measurement time appropriate. And you can see that some, where are we? It stopped updating. Press start again. You can see that some of the peaks are varying. So this is where I can average. So I press the average button. And what I should see is now the data, those peaks are now averaging to their mean. But if you notice, the picture is still updating. It hasn't taken 10 averages and stopped. That picture is moving. And what that allows me to do is roam with my accelerometer, where I'm going to increase the cavitation. And you should see the carpet level come up. We'll give that a whirl. There we are. We've made a change. So straight away, without taking my hands off the machine and on the controls of my analyzer, I can change things on the machine and look at what it does for the spectrum. I've used this on testing gas turbines. So I used to test gas turbines in aircraft, and you could go to an engine setting, write down the overall acceleration level, go to the next engine setting, write down the level, without ever touching your analyzer. Poor little pump is having a fit here, so I'll remove the cavitation. And you can see the picture updating. And as I said, that picture is the average of 10 readings, and you're taking another reading, throwing away the first. So it's smoother, it's more statistically correct, but it changes, it updates. Happy days. Get rid of the noise. Look for Daisy. So that's an exponential averager. Need to press on. So there we go. So just for fun, I've taken a couple of spectra there, one with low res and high res, so you can see the carpet. Just one important point about this carpet that some people often refer to, this random type of part of the signal. I've got two spectra there that I've recorded from this cavitating pump, and pictorially the carpet looks lower for the higher resolution spectrum. And you can play games with the peak to carpet. I'm going to mention that a little bit later. The last common type of averager is something called a peak hold average. Why it's called an average, I don't really know. It's nearly always put in the averager section, but it should really be called a peak hold algorithm rather than an average, because you're not really doing any averages in the true sense of the word. All you're doing is taking a measurement and holding it. If another measurement comes along that's higher, you hold that high value. It's used in acoustics for drive-by and fly-by. So if you're going to measure the noise of a motorbike, for example, you put two traffic cones 100 meters apart. You're standing there with your sound level meter or your FFT analyzer. You see the motorbike go past the first traffic cone. You open your eyes, you press measure. The motorbike goes past. The spectrum will come up as the motorbike goes by. And as you see it go past the second traffic cone, you press stop. And that's deemed to be the noise of that motorbike, that motor car, whatever you're doing. That's not going to be used in machinery health. So why would it be useful in machinery health? It's really useful when you're balancing a machine. If you're going to balance a machine, what you really don't want is to run the machine at a resonant frequency. Balance runs fail when people try to balance machines when they're running at a critical speed. So we can use this peak hold average as a really quick way to determine what the critical speeds are. So back to my lovely blue electric motor. We'll do a quick rundown test, a quick demonstration of that. We'll plug the accelerometer on the bearing, plug my accelerometer back in, and we'll set up for a peak hold average, which you need to be able to see. So here we go. So we'll exit out of that. So we'll set up for our next type of average. So I'm going to come down here, expand my menus. Now I'm going to run down. This machine runs at 3,000 revolutions per minute. So 10,000 hertz is not relevant. We need a 100 hertz frequency range for this demonstration. So 100 hertz. At the moment, you can see here that the acquisition time is 8 seconds, and the machine takes 40 seconds to run down. So we're going to get smearing. So we really want to speed up the rate at which we acquire data. And one way I can do that is to reduce the lines of resolution. So I've reduced it to 100 lines of resolution. That means that my acquisition time is going to be 1 second. I need to change the average type to this peak hold. So we're going to hold the maximum peak. And I can speed things up a little bit more by using this thing called overlap, which I am going to explain. I'm slowly working down these controls to explain them all. Now, one measurement is going to take 1 second. It takes about 40 seconds to run down. So this is an example where I might dial in maybe 60 averages. Whoops, not 69. 60 averages to get that time period. So that should be good. So do a practice spin, nothing trapped. So we'll start the machine. So my machine's running up. I press start. Wonderful. So there's my peak. In America, you would get that at 60 hertz. Here's it running at 50. And we're going to track the machine now to make it slow down. There's a bit of a switching spike came through on this demonstration. It didn't do this morning, but not to worry. So this peak here, this unbalance is moving left as the machine gets slower and slower and slower. And right now I can feel my desk is starting to vibrate because the levels have gone up. It's hitting the natural frequency of my desk. And you can see how the peak hold average is keeping a record of where the levels have been versus time. So it really is a quick and dirty way of doing a rundown. So the levels were coming down, as we would expect, but now they're going back up as it hits a natural frequency of my desk. They're coming down, they're going back up. So you can see all these areas here where they go down, because the unbalanced forces are related to the forces and the displacements. So you can see the levels going down in true cookery program style. Here's one I prepared earlier. This is real data, and what I've done here is taken the trouble. I fitted an accelerometer to my machine. I fitted an accelerometer to my desk. So I've got two. I've got above and below the mount. It's got rubber feet on it. So now I can do my rundown test and see where the critical speeds are. We have customers, many customers, who do balancing as their everyday job. They balance hundreds of machines a day. And the first job of work before they start balancing is to do a rundown test using a peak hold average to find out where the critical speeds are, and then they will do the balancing at a speed that's not on a critical speed. So really useful if you know how it works. What's next? What's next is synchronous time averaging. Let's go back to our power station. Power station, hydroelectric power station, is a good example where I have used synchronous time averaging very successfully, because in certain power stations the noise, the background vibration coming from all this turbulent water completely obliterates and masks the signal that you're trying to detect from your machine of interest. You can get situations where this can happen in other situations other than power stations. Anywhere where you've got a weak foundation. I'm thinking of ships, aircraft, oil platforms. If you've got machines up mezzanine, what you can do is put your accelerometer on a machine of interest, and you will get vibration being transmitted through the deck and up into that machine. It can be quite intrusive. I was on an oil platform many years ago. I was in the ventilator fan room. I had my hardware hat on, my ear defenders on. I was taking readings off a machine and writing them down. And when my eyes got used to the gloom, I could see that the shaft wasn't rotating. I was taking readings off a machine that was stopped. And yet when you put your fingers on it, you could feel your fingers tingling. And it was a classic example of how vibration can transfer through the structure and pop up. These two slides are out of sequence, so I do apologise. Another example is this was a job we did some years ago, where the two machines were talking to each other. There was two machines, 1,500 revolutions per minute each, two bladed impellers, and there was a beat frequency. The two machines were interfering with each other and creating a beat frequency, and that beat frequency was something like 18 revolutions per minute. That was coinciding with the natural frequency of the structure and causing cracking. So as I mentioned earlier about beats, it does happen. It can happen on aircraft engines. As I said, listen to the aircraft engines as you fly home, fly to your holidays. Now, it would be nice to ask the pilot to switch off one engine while you measure the other, which isn't very realistic. Or it would be nice to say to your customer, switch off that pump while I measure this pump. In situations where you can't do that, this is where synchronous time averaging comes in very useful. By the way, sorry, that was out of order. This is Dan Russell's animation. So all credit to Dan Russell, showing how beat frequencies work. You've got two signals that are very close together in frequency. They will go in phase and add and make a high vibration or a high noise level. They'll go out of phase and cancel each other out. So you get this third frequency being generated called a beat frequency. So you can see what's going on. Now, ideally, you'd switch one of them off so you can measure the other, but you can't always do that. So, what do? I have a little demonstration for you. The first thing you need to do is get yourself a 1 pulse per revolution signal off the machine. So I've got an accelerometer mounted on my machine of interest, and I've mounted a piece of reflective tape. So you can see that on my electric motor. I've got a piece of reflective tape on my electric motor, and it has to be 1 pulse per rev because we're going to grab readings synchronously with the shaft. You mount your accelerometer in the normal way, and the way synchronous time averaging works is the piece of paper, the piece of reflective tape comes round, and you get a pulse, and you open your eyes and you grab a measurement. That measurement will have interference, the noise on it. But the next time the piece of tape comes around, you grab your next measurement and you take your next block. Now this is why it's called time averaging, because it's done in a time domain. You take your time domain block of the first measurement and your time domain block of the second measurement, and you add the two together and divide by 2. And what will happen is that the non-synchronous noise, the random noise, the other machine will have shifted its position slightly. So when you add the two together, the noise starts to disappear. And I've tried this in anger, and it works extremely well. It's very, very powerful. Sorry I haven't got a live demonstration for you, but I do have a real demonstration for you. This is real data, and it's taken off this actual machine to simulate what we've got. So on the top left, we have the unbalance from the machine that we're interested in. And what I've done is I've added in interference, and I've done that by having a little vibrator in a box. So that's the signal coming off our non-synchronous machine. A machine of it's interfering, and I actually used some. There we go, high-tech blue tack, and stuck that on my machine to simulate the interference. And you run the machine up, switch the noise on, and there is the signal with the noise on it. Now, if you take the spectrum of that, you will make a misdiagnosis, because the machine, as we've already seen, is out of balance. But because of the interference, we get quite a lot of harmonics. So my diagnosis would be that the machine is mechanically loose, maybe even misaligned. So I make a misdiagnosis due to the fact you've got all this other signal there. So what do? You do synchronous time averaging. You get your piece of reflective tape. You get a 1 pulse per revolution signal. Every time that pulse comes around, you grab a time block. And just for a practical point, if you are going to do this, I can recommend something like 40 or 50 time averages. Once you've cleaned the signal up in the time domain, you can then do the FFT. So I haven't cheated. This is real data. I've cleaned the signal up, and we're back now to just the unbalance. We've removed, by doing this process, so there it is. There's the signal with noise. Synchronous time average, you remove all the non-synchronous. And I've heard people, experts who use this, you can get a 12 decibel to 20 decibel improvement. 12 decibels is around about just over 3 times, and 20 decibels is about 10 times. So between a 3 and a 10 times improvement in your signal to noise when you do synchronous time averaging. Last 15 minutes. Right, averaging at low speed. All averaging is good stuff. We've got RMS, which is just a simple start, stop, store it type. We've got exponential, which is a moving average, good for roaming and investigations and data that's changing. We've got peak hold, which is good for determining critical speeds. And we've got synchronous time averaging, which is good at cleaning signals up. Life becomes slightly different when we start working at slow speeds. This balancing act that we have between the number of averages and the length of time it takes, we have to give very careful consideration. And there are pros and cons, advantages and disadvantages, which is the original title of this session. One thing that affects this is something that's called windowing and overlap. So we need, before we can talk about averaging a slow signal or a long time period signal, we need to understand 2 things. We need to understand something about Hanning, and we need to understand something about overlap processing. So I have a little demonstration for you of Hanning. It's a video. What I've done is I've got an accelerometer on my machine, And I've used an analyzer where I can demonstrate Hanning to you. And what I'm going to do is disappear briefly and run you through the video. So here we go. Whoops, daisy. So let's pause that. So that's the signal from my electric motor. On the right hand side you are seeing the time domain trace. You've got vibration acceleration on the y-axis, you've got time on the x-axis, just as same as an oscilloscope trace. And we're taking that signal, doing the FFT, and on the left-hand side you've got acceleration versus frequency. Now, one problem with this, and it occurs on all FFT analyzers, it doesn't matter whose, you get something called a truncation error. We've opened our eyes, we've opened a switch, we've allowed data in, we've closed our eyes, we've closed the switch, we've stopped taking data, and that creates a step function at either end of our signal. And the frequency analysis of that step function gives us lots of sidebands on our spectrum, and those sidebands aren't actually there. It's called the truncation error. So we need to cure that problem, and by far the most popular way of curing that problem is to use something called a Hanning weighting window. So what you're going to see me do on this video is I'm going to switch on some Hanning weighting. Lovely stuff. So the Hanning, mathematically, that's actually what you're doing to the signal. When you look at a time domain trace on an FFT analyzer, you don't normally see this. It's actually done hidden in the background so that we don't worry about it. But when it comes to certain types of measurement, you need to be mindful that that is actually what is being measured and analysed on your analyzer. The beauty of getting rid of the step function at either end of your window means that we get rid of these sidebands that were false, and we get rid of the truncation error. The trade-off is you get a little bit of width to your analysis. If I finish the job off and finish playing the video, we zoom in on this part. In fact, what I think I'm going to do is 10 to the hour. So I'll finish it off. So we can see that the top of the peak had a triangular type of effect. If we go to flat top, what happens with flat top is a differently shaped width, different shaped window, and the spectrum gains some width, but the accuracy of our amplitude measurement is much better. So with a Hanning weighting window, that reading was 12.2 millimeters per second. With a flat top weighting window, it's 12.6. The reading has gone up slightly. So we use a flat top weighting window when we want good amplitude accuracy. I've kind of rushed that a little bit. We'll zoom in just to finish. There we go. The reason why it's called a flat top weighting window is that the spectral peak has a flat top to it. So we lose out on the frequency resolution, but we gain on the amplitude resolution stroke accuracy. Sorry, I kind of breezed through that. Where are we? There we go. Hello again. I kind of breezed through that because the salient point, the relevant point, is the fact that we've got this Hanning weighting window. And on the normal circumstances, what you would do if you're doing 1, 2, 3, 6 averages, you would take your Hanning weighted data, do the FFT, store it, do another one, add it to the memory, store it and divide by 2, and do that 6 times. You've got the average of 6 measurements. This works for a continuous signal, but starts to fall down, come unstuck, give you problems if you're dealing with transients. Because that transient could well fall in between 2 of your Hanning weighted windows. And there's 2 approaches to resolve this problem. One approach is to use something called overlap processing. Because what you're doing is mathematically you're throwing away some of this data to remove the truncation. So you're mathematically throwing it away. And there's a school of thought which says, well, why don't you keep it and do some maths on that number or those numbers? So when you dial in overlap processing, you start to remove any gaps in your data. And that has the effect of speeding up your measurement. So if we go to, excuse me a second, if we go back to our analyzer, I'm going to try and do this really quickly. We'll do it on my electric motor. So to save time, I need to get this done within the hour. So I'm just going to recall a straight velocity measurement. We'll go down to our averages section. And to give me time to talk, I'm going to ask for 20 averages. And this is where the overlap control is. We'll do a ordinary RMS average. So 800 lines, RMS averager, and no overlap, and 20 averages. So if I start my signal, move that around so I don't hurt myself. Start my signal. So start my machine and start my measurement. So what's going to happen is it's going to take 16 seconds to do these measurements because we're taking the data sequentially. And while it does that, this is a real advantage when you're doing your route-based data collection, your route-based data collection. 16 seconds can be an awful long time to do your averages. If you multiply that by 2,000 measurement points, you're going to be spending a lot of time. So I'll switch on the average. You should, with a little bit of luck, look at the amount of time it's taken. Which should work out at around about 16 seconds. There we are, it's done it. That took 16 seconds, which felt like an awfully long time. So what we can do is we can speed up our acquisition by using overlap processing. So if I go back to my menu and we go back to our averager control, now, so a lot of people use 50% overlap. I'm going to speed it up even further and go to 75 because time's marching on. So now, instead of taking 16 seconds, it's going to take 4.6. So I press start. Switch on my average. Measure the length of time. Should take about 4 seconds. Done. So it's taken 4 seconds instead of 15 seconds. So overlap processing radically speeds up the rate at which you can harvest your route-based data collection whilst keeping that data statistically correct, all the good stuff that we get from averaging. Right, so that was that. Now then, we've got to be careful when we're dealing with pulses. We've got a bearing here. If we've got damage on a bearing, we're going to get some kind of impact, some kind of pulse, and there's a balancing act. And it all boils down, frankly, my dears, to personal preference. And the analogy I use is measuring your own pulse. We've got pulses coming off bearings, we've got pulses coming off human beings. As a hobby, I am a first aider, and if I'm called upon to look after somebody who's ill, one of the early jobs of work that you need to do is measure somebody's pulse. This is audience participation, ladies and gentlemen. You can all do this yourselves. What I want you to do is measure your own pulses. I want you to put your fingers on your radial pulse. It's just in line with your thumb. And I want you to measure your pulse. Now, if you're measuring somebody's pulse, what the textbooks say is that you should do it over at least 30 seconds. So you get a good average, because what can happen is people can miss a pulse if they've got heart problems. So you would average over 30 seconds. If it's unsteady, you certainly want to average over 60 seconds. So instead of taking 2 pulses, writing down the time interval, and then taking 2 more pulses and writing down the time interval, and taking 2 more pulses and writing down the time interval, what you would do more realistically is take a representative set of pulses. And that is the method that certainly SKF recommends if you are trying to measure pulses coming from a slow machine. Because my heart rate, let's just give it a quick feel. I've lost it, I'm dead. There we go. I'm slightly stressed, so it's normally about 60 per minute, slightly higher, because I'm stressed looking to a webcam. But that's not uncommon from a rolling element bearing. One impact per second, or even slower. So if you're taking the pulse of a bearing, you want to do a good job and take a representative set of those pulses. There are 2 ways that you can do it. There's the method where you can use overlapping. So you take a series of overlapped measurements. So if you look at the horizon of the measurements, you can see that we've encompassed all of the pulses. And there's a school of thought that says you take one long measurement. When you look at the actual maths, there's very little difference. If you compare apples for apples or oranges for oranges, as far as signal to noise goes, there is very little difference. But one difference it does make is the resolution of your reading. And I think I have some data here. It's nearly time up on the hour. So if you forgive me, rather than doing the demonstration live, which will take us an extra 10 minutes, I've pre-recorded this data. What I've done to simulate my bearing damage, I've got a bolt here, and I can scrape the bolt once a second to simulate that damage. And there's no limit to how slow you can go. It's all a matter of dialing in the appropriate lines of resolution or the number of averages, whichever method you prefer. Now there are advantages and disadvantages to both. If on the left hand side I have taken a 400 line spectrum, I've taken 7 averages with 50% overlap, which gives me a 16-second measurement. So you can see I've just got over 3 and a bit of those pulses, and on the lower trace you've got the spectrum. Now there's a variety of methods of determining bearing wear, and this is all very well written up in application notes. But one method that some people use is to look at the difference between the peak coming from the bearing damage and what they call the carpet. So if you're really interested in getting a statistical, a representative statistical measurement of where the level of the carpet is versus the peak, then averaging, as I previously explained, is possibly the way to go, because the random part of the signal will average to its mean, leaving you with the periodic. There's lots of information and techniques that SKF uses, which relies on the harmonic content of the signal. There's even a patented method called a harmonic activity indicator. The presence of harmonics and sidebands in your measurement is really good evidence that you have got bearing damage. So you can see with a 400 line spectrum, because the resolution is lower, I can't see those harmonics. But if I do a 1600 line spectrum, because I've taken a more representative set of readings over one time block, I can go to much higher resolution. So on the right hand trace, I've taken one average of 1600 lines over 16 seconds, and you can see those harmonics. By all means, averaging is great. I'm not arguing with that. Averaging is fantastic, but at slow speeds it can become an issue, because if it's taking 16 seconds to get you one really good quality measurement, and you're going to average 4 averages, 4 times 16, that's over a minute that you're going to be standing next to your machine, and is it realistic to expect that machine not to have varied speed during that time? So it's this balancing act, this trade-off between the two. If you get goosebumps looking at logarithmic scales, there it is in logarithmic scale. With a logarithmic scale, it's easier for your eyeball. Remember, I was talking about eyeball averaging and common sense and putting your eye through it. It's easier for you to eyeball average the data to look at where this thing called the carpet is versus your peak, but you can't see the harmonics. Whereas on this peak, it's more difficult to see the carpet, but it's easier to see the harmonics. Whatever method you prefer, certainly SKF recommends the right-hand method for measuring slow speed machines. That is me scraping a bolt. This is real data taken from a machine. So this is, I can't remember, I think it was, well, it's just, I do know it's a very large slow speed bearing with some damage on it. If you measure over 3 seconds, and you get 2 pulses, when you look at this, the spectrum, the ability to see those sidebands is reduced because the resolution is quite low. If you take the measurement over 16 seconds, so you get 10 to 12 pulses is what we normally say. You take the measurement over 16 seconds, we get a much higher resolution spectrum, and we can see those sidebands. And that's, as I said, it's really good evidence that we've got damage. Right, that is the hour, bang on the dot. Managed to get through it. It was 1 hour 5 minutes on the last one. It's 1 hour on this one. So for the benefit of those of you who are watching the video, thanks for sparing your time, and cheerio. Goodbye.